relation, which is called the vector product. Or also called, most of the time I refer to it as the cross product. The cross product is written like so: A cross B equals C. It's a cross. Very clear cross. Now I'll tell you how I remember that is method number 1. I'm going to teach you just like with the dot product program. I will tell you method number 1, which is the one that always works. Time consuming, but always works. You write down here a matrix with 3 rows. The first row is X roof, Y roof, Z roof. The second one is A of X, A of Y, A of Z. It's important if A is here first, that second row must be A. And the third row is then B. B of X, B of Y, B of Z. So these are numbers, and these are unit vectors. I'll repeat this here, verbatim. You'll see in a minute why I need that. And I will do the same here. Okay, and now comes the recipe. You go from the upper left-hand corner to the one in this direction. You multiply them all 3, and that's the cross sign. So you get AY, so C, which is the cross, A cross B, equals AY times BZ times the X roof. But I'm not going to put the X roof in yet, because I have to subtract this one, minus sign, which has AZ dy. So it's minus AZ dy, and that is in the direction X. The next one is this one, AZ dx, minus this one, AX bz, in the direction Y. And last but not least, AX dy minus AY dx in the direction of the unit vector Z. So this part here is what we call C of X. It's the X component of this vector. And this we can call C of Y, and this we can call C of Z. So you can also write that vector then as C equals C of X, X roof, plus C of Y, Y roof, plus C of Z, Z roof. Cross product of A and B. We'll have lots of exercises, lots of chances you will have on assignment 2 to play with this a little bit. Now comes my method number 2. And method number 2 is again, as we have with the dot product, is a geometrical method. Let me try to work on this board in between. If you know vector A, and you know vector B, and you know that the angle is theta, then the cross product C equals A cross B is the magnitude of A times the magnitude of B times the sine of theta. Not the cosine of theta as we had before with the dot product, it is the sine of theta. So we can already immediately see that this will be 0 if theta is either 0 degrees or 180 degrees. Whereas the dot product was 0 when the angle between them was 90 degrees. This number can be larger than 0, if the sine theta is larger than 0, it can also be smaller than 0. Now we only have the magnitude of the vector, and now comes the hardest part, what is the direction of the vector? And that is something that you have to engrave in your minds and not forget. The direction is found as follows. You take A, because it's first mentioned, and you rotate A over the shortest possible angle to B. If you have in your hand the corkscrew, and I will show that in a minute, then you turn the corkscrew as seen from your seats clockwise, and the corkscrew will go into the blackboard. And if the corkscrew goes into the blackboard, you will see the tail of vector, and you will see a cross, a little plus sign, and therefore we put that like so. A cross product is always perpendicular to both A and B. But it leaves you with 2 choices. It can either come out the blackboard or it can go into the blackboard. And I just told you which convention to use. And I want to show that to you in a way that may appeal to me more. This is what I've used before on my television help sessions that I've given at MIT. I have an apple, and not an apple, this is a tomato. Not a tomato, it's a potato. I have a potato here, and here's a corkscrew. There's a corkscrew. I'm going to turn the corkscrew as seen from your side clockwise. And you'll see that the corkscrew goes into the potato in. That's the direction then of the vector. If we have B cross A, then you take B in your hands and you rotate over the shortest angle to A. Now you have to rotate counterclockwise. And when you rotate counterclockwise, the corkscrew comes to you. There you go. And so the vector is now pointing in this direction. And if the vector is the easiest part of 801. Let's take an extremely simple example. Again, I don't mean to. It shows you, it's such a simple example that you will get chances, more advanced chances on your assignments. Suppose I give the vector A is x roof, is a unit vector in the x direction. That means A of x is 1. And A of y is 0 and A of z is 0. And suppose B is y roof. That means B of y is 1. And B of A is 3 of x is 0 and B of c is 0. What now is the dot product, the cross product A cross B? Well, you can apply that recipe, but it's much easier to go to the x, y, z axis that we have here. A was in the x direction, the unit vector, and B in the y direction. I take A in my hand, I rotate over the smallest angle, which is 90 degrees to y, and my corkscrew will go up. So I know the whole thing already. I know that this cross product must be z roof. The magnitude must be 1, that's immediately clear, but I immediately have the direction by using the corkscrew rule. Now, if you are very smart, you may say, aha, you find plus z only because you have used this coordinate system. If this axis had been x, and this one had been y, then the cross product of x and y would be in the minus z direction. Yeah, you're right. But if you ever do that, I will kill you. You will always have to work with what we call a right-handed coordinate system. And a right-handed coordinate system, by definition, is one whereby the cross product of x with y is z, and not y minus z. So whenever you get in the future involved with cross products and torques and angular momentum, always make yourself an x, y, z diagram for which x cross y is z. Never, ever make it such that x cross y is minus z. You will hang yourself. But for one thing, that wouldn't work anymore. So be very, very careful. Must work, if you use the right-hand corkscrew rule, make sure you work with the right-handed coordinate system. Alright. Now the worst part is over. And now I would like to write down for you, yes, you can pick up some of the fruits now, although it will penetrate slowly. I want to write down for you equations for a moving particle, a moving object in three-dimensional space. A very complicated motion, which I can hardly imagine what it's like. It is a point that's going to move around in space. And it is this point P. This point P is going to move around in space, and I call this vector OP, I call that now vector R, and I give it a sub-index T, which indicates it's changing with time. I call this location A of Y, I'm going to call that Y of T. It's changing with time. I call this X of T, is going to change with time, and I call this point Z of T, which is going to change with time, because point P is going to move. And so I'm going to write down the vector R in its most general form that I can do that, R, which changes with time, is now X of T, which is the same as A of X there before, times X roof, plus Y of T, Y roof, plus Z of T, Z roof. I've decomposed my vector R into three independent vectors, each one of those changes with time. What is the velocity of the particle? Well, the velocity is the first derivative of the position, so that is dr dt. So there we go. What's the derivative of this one, which is dx dt of x roof. I'm going to write for dx dt x dots because I'm lazy, and I'm going to write for d2x dt squared x double dots. It's often done, but not in your book. But it's a notation that I will often use, because otherwise equations look so clumsy. Plus y dot times y roof plus z dot times z roof. So z dot is dg dt. What is the acceleration as a function of time? Well, the acceleration as a function of time equals dg dt. So that's the second derivative of x versus time, and so that becomes x double dot times x roof plus y double dot times y roof plus z double dot times z roof. And look what we have now accomplished. It looks like minor, but it's going to be big later on. We have a point P going in three-dimensional space. And here you have the entire behavior of the object as it moves its projection along the x-axis. This is the position, this is its velocity, and this is its acceleration. And here you see the entire behavior on the z-axis. This is the position on the z-axis, this is the velocity component in the z-direction, and this is the acceleration in the z-axis. And here you have the y. So in other words, we have now a three-dimensional motion we have cut into three one-dimensional motions. This is a one-dimensional motion. This is a behavior only along the x-axis. This is a behavior only along the y-axis, and this is a behavior only along the z-axis, and the three together make up the actual motion of that particle. What have we gained now? It looks like a mathematical zoo. You would say, well, if this is what it's going to be like, it's going to be hell. Well, not quite. In fact, it's going to help you a great deal. First of all, if I throw a tennis ball in class, like this, then the whole trajectory vector is in one plane, in the vertical plane. So even though it is in three dimensions, we can always represent it by two axes, by two-dimensionally, a y-axis and an x-axis. So already the three-dimensional problem often becomes a two-dimensional problem. We will with great success analyze these trajectories by decomposing this very complicated motion. Imagine what an incredibly complicated arc that is. And yet we are going to decompose it into a motion in the x direction, which lives a life of its own, independent of the motion in the y direction, which lives a life of its own. And of course you always have to combine the two to know what the particle is doing. We know the equations so well from our last lecture for one-dimensional motion with a constant acceleration. The first line tells you what the x position is as a function of time. The index t tells you that it's changing with time. It is the position at t equals 0 plus the velocity at t equals 0 times t plus 1/2 axt squared, if that is an acceleration in the x direction. The velocity immediately comes from taking the derivative of this function, and the acceleration comes from taking the derivative of this function. Now, if we have a motion which is more complicated, which reaches out to 2 or 3 dimensions, we can decompose the motion in 3 perpendicular axes, and you can replace every x here by a y, which gives you the entire behavior in the y direction, and if you want to know the behavior in the z direction, you replace every x here by z, and then you have decomposed the motion in 3 directions. Each of them are linear. And that's what I want to do now. I'm going to draw an object, a golf ball or an apple, in 2600, and we know that it's in a vertical plane, so we already here is a two-dimensional problem. This being, I call this my x-axis, and I'm going to call this my y-axis. I call this the increasing value of x, and I call this the increasing value of y. I could have called this increasing value of y. Today I've decided to call this increasing value of y. I'm free in that choice. I throw up an object at a certain angle, and I see a motion like this, going and it comes back to the ground. My initial speed when I do it was v0, and the angle here is alpha. The x component of that initial velocity is v0 cosine alpha, and the y component equals v0 sine alpha. So that's the begin velocity of the x direction, which is the begin velocity in the y direction. A little later in time, that object is here at point t, and this is now the position vector, which we have called r of t. That's this vector. That's the vector that is moving through space. At this moment in time, x of t is here. And at this moment in time, y of t is here. And now you're going to see, for the first time, a big change by the way that we have divided the two axes here. An independent line, first x. I want to know everything about x that has to be known. I want to know where it is at any moment in time, velocity and the acceleration, only in x. First, I want to know that at t equals 0. Well, at t equals 0, I look there. x0, let's see, I can choose that to be 0. So I can say x0, 0, that's my free choice. Now I need v0x. What is the velocity? The velocity at t equals 0, which we have called v0x, is this velocity, v0 cosine alpha. And is not going to change. Why is it not going to change? Because there is no a of x. So this term here is 0, we only have this one. So at all moments in time, the velocity in the x direction is v0 cosine alpha. And the a of x equals 0. Now I want to do the same in the x direction for time t. Well, at time t, I look there at the first equation. There it is. x0 is 0. I know v0x, that is v0 cosine alpha. So x of t is v0 cosine alpha times t. But there is no acceleration, so that's it. What is vx of t? The velocity in the x direction at any moment in time. That's that equation. That is simply v0x. It is not changing in time, because there is no acceleration. So the initial velocity at t0 is the same as t seconds later, and the acceleration is 0. Now, we're going to do this for the y direction. And now you begin to see the gain for the decomposition. In the y direction, we change the x by y. And so we do it first at t equals 0. So look there. If it becomes y0, I call that 0. I can always call my origin 0. I get v0y times t. Well, v0y is this quantity, v0 sine alpha. v0 sine alpha. This is v0 sine alpha. That is the velocity at time 0, and this is 0. At time 0. This is 0 at time 0. What is the acceleration in the y direction at time 0. What is the acceleration? That has to do with gravity. There is no acceleration in the x direction. If you can believe that there is one in the y direction. So only when we deal with the y equations does this acceleration come in, not at all when we deal with the x direction. Well, if we call the acceleration due to gravity g equals plus 9.80, and I always call it g, what would be the acceleration in the y direction, given the fact that I call this increasing value of y? Minus 9.8, which I will also say always call minus g, because my g is always positive. So it's minus g. So that tells the story at t equals 0 in the y direction, and now we have to complete it at time t equals t. At time t equals t, we have the first line there, y0 is 0, so we have y as a function of time, y0 is 0, so we don't have to work with that. Where's my? So this is 0, so I get d0y times t, so I get d0 sine alpha times t, plus 1/2, but it is minus 1/2 gt squared, and now I get the velocity in the y direction at time t, that is my second line, that is going to be d0 sine alpha minus gt, and the acceleration in the y direction at any moment in time equals minus t. And now I've done all I can to completely decompose this complicated motion into two entirely independent one-dimensional motions. And the next lecture, we're going to use this again and again and again and again. This lecture is not over yet, but I want you to know that this is what we're going to apply for many lectures to come, the decomposition of a complicated trajectory into two simple ones. Now when you look at this, there is something quite remarkable. And the remarkable thing is that the velocity in the x direction throughout this whole trajectory, if there is no air drag, if there is no friction, is not changing. It's only the velocity in the y direction that is changing. It means if I throw up this golf ball, I throw it up like this, and it has a certain component in x direction, a certain velocity, if I move myself with exactly the same velocity, with exactly the same horizontal velocity, I could catch the ball here. It would have to come back exactly in my hands. That is because there is only an acceleration in the y direction, but the motion in the y direction is completely independent of the x direction. The x direction doesn't even know what's going on in the y direction. In the x direction, if I throw an object like this, the x direction simply, very boringly, moves with a constant velocity. There is no time dependence. And the y direction on its own does its own thing. It goes up, comes to a halt, and it stops. And of course the actual motion is the sum, the superposition of the two. We have tried to find a way to demonstrate this quite bizarre behavior, which is not so intuitive, that the x direction really lives a life of its own. And the way we want to do that is as follows. We have here a golf ball,